This video is about logarithms. Logarithms are a useful technique to solve many equations in physics, mathematics, chemistry, and related subjects. Let's first see what the definition is. Any exponential equation can usually be converted to its corresponding logarithmic equation. So you must already be familiar with uh, exponential equations, things like 5 power 3 is equal to 125. Therefore, if you have a power x equals y, then by definition, you will have log y to the base a equaling to x. The way to visualize it is think about how many times does a need to be multiplied with its own self, that is with a itself, to get y. Clearly, that should be the exponent of a so as to get y. For example, if you multiply 2 5 times to its own self, what I mean is 2 times 2 times 2 times 2 times 2, then you will get 32. Therefore, 2 power 5 should equal 32. Or, correspondingly, you can see that log 32 to the base 2 is equal to 5. Now, let's see some examples of this. Since 8 equals 2 cube, you can just compare this form of logarithm with this equation given over here. Since you know that 2 power 3 is equal to 8, therefore log 8 base 2 should be equal to 3. And since half is equal to 2 power minus 1, you will have the value is equal to minus 1. So remember that the base in the exponent equation remains the base in the logarithmic equation. That is a good mnemonic to uh, understand this and even remember it. We have some common bases in which logarithms are expressed. Based upon the area of study, the choice of base might differ. For example, in chemistry and a lot of the common fields of study, we usually take log to the base 10 because we work with denary numbers, and 10 is usually a good number to a good base to actually work with such numbers. E is an irrational number which approximately equals 2.718. That is only an approximate value, and this is called the natural logarithm. This is more suited for scientific calculations whenever we work with things like integration and differentiation. We will usually be involving logarithm to the base e. And then we have base 2, which is a binary logarithm. If you're into algorithms and if you want to evaluate running complexity of algorithms, usually binary numbers are preferred over there. So you can evaluate the logarithm in base 2. First of all, the thing to understand is that all these bases can be converted to each other. But we will, in the scope of physics, we will usually stick to base e. Let's quickly see some properties of logarithms. Logarithms is a big topic and its properties are enormous. But from a physics perspective, some of the most frequently used properties are listed here. So we will have the product property first. Log of AB equals log A plus log B. For example, take A as some 4 and B as 16. Now, 4 into 16 is 64. Let's think about it. Let's say that the base of this logarithm was 2. So A into B over here gives us 4 into 16, which is 64. 64 to the base 2 is basically equal to 6. You will get that as log 4 base 2, which is 2, plus log 16 base 2, which is 4. So you will get 2 plus 4 equals 6. Because we have the exponent law that a power m times a power n equals a power m plus n, if you write the equivalent logarithmic law using this definition over here, you will boil down to this logarithmic relation. And similarly, making use of the other exponent law that a power m, the division law that a power m by a power n equals a power m minus n, we can similarly prove that log of a by b equals log a minus log b. The third is one of the most used properties, that if in the argument you have an exponent, then that exponent comes out, which means log a power n will equal n times log a itself. Well, you can think of 3 as a special case of 1. Uh, think of, let's say for example, take b also equal to a. In that case, we will have log of a into a, which is log of a square. So that should equal, by definition, log a plus log a. Now log a plus log a is nothing but twice of log a, which you can get even from this formula, which n will equal 2, so we'll get 2 times log a. And you can repeatedly do this. You can prove it using principle of mathematical induction in general. And fourth property, this is especially useful when we are doing things like definite integration, or we are trying to evaluate a particular limit, that log 1 is basically 0. This is based on the fact that a power 0 is 1. So I think this is pretty much enough for physics. Uh, One thing to understand over here is that I have not specified the base to which this logarithm is calculated. It's because these properties and almost all the properties of logarithms that do not specify the base are valid for any base. So you can take the base of the logarithm as 2, 10, e, or any real number of your choice. When I say real number, there are some restrictions on that. You should only take positive real numbers, and it should not equal 1. These are valid for any base. Let's just see a practical case of this logarithm being employed in physics. So if you have a cylindrical capacitor, its capacitance is given by this particular formula. Now, there are many terms involved in this formula, and this is not really a video on capacitance. So I will not be explaining all the terms, but you can see the thing of interest over here is this logarithmic term. Ln, you would remember, is the natural logarithm. So a cylindrical capacitor has two radii, an inner radii, which is inner radius, which is small r, outer radius, which is capital R. So first we take the ratio of those two, and then we take the natural logarithm of that. And this is employed in the formula for capacitance of a cylindrical capacitor, which is measured in farads, the SI unit of this system. That is it from this video. Thank you.